Assalamualaikum and very good morning. We are from Group 7, want to present about the 66 kV SLPE termination defect analysis cavities. So this is our team members, Hari Akmal, Amir Haziq, Muhammad Haikal and Muhammad Akil Iman. For the table of contents, we have 4 parts: introduction, methodology, result and discussion, and conclusion. We move to the first part, introduction. First, background. High voltage cable termination provide a safe connection between power cables and electric equipment. Proper electric field control is required to prevent insulation failure. However, cavity defects can cause electric field concentration, leading to partial discharge PD, activity and insulation degradation. Second, we move to the problem statement. Cavity defects disturb the electric field distribution within cable termination. The resulting field enhancement increases the risk of partial discharge and reduces system reliability. Therefore, the impact of cavity defects on a 66 kV SLPE cable termination must be investigated. We move to the objective. The study aims to analyze the electric field distribution of a 66 kV SLPE cable termination, quantify the field enhancement caused by cavity defects, identify potential PD, inception location, and evaluate the design based on the IEEE STD 404 and IEC 60840. We move to the last part is the cable termination parameters. The cable model consists of 200 mm squared conductor, SLP insulation, semiconductor layer, a metallic shield, and outer jacket. A cavity defect is introduced at the stress, cone interface and analyzed using film. The design is based on IEEE ST 404 and IEC 60840 standards for high voltage cable accessories.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. My name is Muhammad Ikram Hussein. My matrix number is DE230118. So I'm from Group 7 for the high voltage. So today I'm gonna present about my part, which is a methodology. Well, the first thing first is about the cable design and construction. So there is a 3 point that I want to show or to tell about. The first thing first is about the design standard. Our project is based on IEC 60840 standard for high voltage cable, and then the layer of structure. It consists of concrete layers, include the copper conductor, semiconductor screens, XLPE insulation, LED, and also the PVC OH DPE jacket. And the last one about the dimensions. We follow the standard sizing by use the size of 9 mm thickness for the XLP insulation layer. And now we move to the methodology, which is the type of cable that we use. For the first thing first, the copper core, which is for the conductor, use a 200 mm square. For the inner semiconductor is 0.8 mm. The XLP insulation, we use a 9.0 mm. The outer semiconductor, we use a 0.8 mm. The metallic shield, which is our team, use the lead, which is 1.0 mm. And the last one is the PVC or HDPE jacket, which is we use the 3.0 mm. And now for the simulation setup to prove our project, which is we use the FEMM for the 2D axiometric model, which is the finite element mathematics. And we have a 2 part, which is the boundary condition and also the material properties. For the boundary condition inside the FEMM that insulator that we use, which is the cable XLPE, the first thing first, the conductor. The value of conductor, we use at 38100 volt because the project that we use is actually is 66 kilovolt. By V line to line, the value is 38,100 kilovolt. 38,100 volt. And now for the grounding, the value is 0 volt. And move to the material properties. The silicon, we put the relative permittivity inside the FEMM is the X consists of 15 and the Y permittivity is consists of 15. For the lead, the relative permittivity, the X and Y also have a same value, which is 1. The copper relative permittivity, the value for the X and Y also the same value as a lead, which is 1. The air also a 1. While for the polyethylene or LDP or HTPE, the relative permittivity for the epsilon x and epsilon y, the value is 2.0, which is we put inside our simulation in FEMM insulator. And the last one about the PVC, the relative permittivity is x equals to y and x equals to 3 and y also equals to 3, which is the permittivity for x and permittivity for y.
Assalamualaikum warahmatullahi wabarakatuh. I'm Haris Akmal bin Pairulani, metric number DE230133. Now I will present my part, which is the result and discussion. So as you can see from the slide, there are two figures. The first one is the simulation for electric field intensity without a cavity. The second one is the with cavity. If we look at the first figure on the left, this represents our baseline model. Here, the electric field is uniform, distributed across the cable insulation layer. The color transition is smooth, meaning the dielectric stress is well managed under normal operating condition. However, when the air cavity is introduced, the field distribution distorts. As pointed out by the arrow, we can see a self-stress concentration forming directly around the air void. This happens due to the permittivity mismatch between the insulation material and air. Moving on to the comparison, this slide shows the electric field intensity graph for two different simulation setups. The comparison and difference, if we compare both graphs, they look similar because both have sharp drop and sudden spike where the cavity is located. However, the main difference is peak value. The graph on the right shows a slightly higher maximum electric field intensity compared to the graph on the left. Finally, this slide shows the comparison of the maximum electric field for different cavity size from 1.0 mm until 2.0 mm. As you can see, when the cavity size gets bigger, the value of electric field intensity also increase. For the 1 mm, the peak value is around 5.25 exponent 6. For 1.5 mm, the value is 5.27 exponent 6, and the highest value is 2 mm, around 5.45 exponent 6. For conclusion, we can also see the pink color area, which represent the highest stress zone, become larger. This proves that the bigger air cavity create the worst electrical stress and more dangerous for the cable insulation. So now for optimization design, looking at the comparison of the graph, as you can see, the design without the PVC layer get the higher maximum electric field compared to the second one. After at the PVC layer, the value is reduced from 5.245 exponent 6 volt to 5.235 exponent 6 volt. This happened because the PVC higher permittivity redistribute and smooth out the electric stress, effectively minimizing the risk of the dielectric breakdown.
Alright, now I'm going to present for the critical reflection and sustainability part. Alright, we start with critical reflection. So FEM simulation successfully analyzed the effect of cavity defects on electric field distribution. Electric field stress was concentrated around A-filled cavities due to the dielectric mismatch between A and XLP. Larger cavity size result in a higher electric field intensity and increased risk of partial discharge. The study was limited to a 2D axisymmetric model under steady-state conditions. Thermal effects, moisture, edging, and transient voltage were not considered. Actual insulation defects may have irregular shapes and locations compared to the idealized model. And then for the sustainability part, the first point is reducing cavity defects improves cable reliability and service life. Lower risk of PD, reduce maintenance and replacement costs. Longer equipment lifespan, minimize material waste and resource consumption. Improve cable performance, enhance power system efficiency and reduce outage. Future improvements may include smart monitoring systems and advanced insulation materials. Alright, now we move on to the conclusion part. We start with the first point, which is FEM was used to investigate cavity defects in a 66 kV XLPE cable termination. Electric field stress was highest near the conductor insulation interface and around cavity defects. Air cavities cause significant electric field enhancement due to their lower dielectric strength. Increasing cavity size from 1 mm to 2 mm increase the maximum electric field intensity. Larger cavities increase the likelihood of partial discharge and also insulation degradation. FEM proved to be an effective tool for predicting defect-induced failure mechanisms. Proper manufacturing quality control and installation practice are essential to prevent cavity formation. The study supports the development of safer and more reliable high voltage cable termination systems. Alright, that's all from me. Thank you.